Okay, so next video, this is related to the Lewis structures, so hopefully you know how to do Lewis structures at this point. We are going to look at, and I don't know that I said this in class, but we're going to talk about that now, the VSEPR or molecular geometry. VSEPR is, what this means is valence, shell, electron, pair, repulsion. This says a lot about valence, shell, electron, pair, repulsion. So VSEPR. This is going to help us figure out which shape our molecules are. So VSEPR is going to give us kind of that idea. So let's talk about electrons in and of themselves. So if I have some kind of central atom and I attach some atom to that central atom, okay, so what we know is I know that this bond, this single bond here, has 2 electrons in it. Right? Those 2 electrons are negatively charged, but they're holding those 2 positive centers together. So there are 2 electrons there. Okay. If I have a lone pair of electrons, and I put this on the other side, I have a couple of questions. So first of all, this is a lone pair, and this is also 2 electrons. So just quickly, a single bond, these are bonding electrons, right? Because those electrons are in a bond. They're holding 2 things together. A lone pair is going to be as known as a non-bonding set of electrons. These are non-bonding. They're not doing any bonding. They're just simply attached to that central atom. So VSEPR, the idea of VSEPR is that electron pairs repel one another. So here's an electron pair and here's an electron pair, and notice that they're opposite side of the central atom. They're in the opposite side because negative is going to move away from negative. So they get as far away from each other around that central atom as possible. Just imagine you had a sphere and you attach 2 things to it. They didn't want to be near one another. They would be on the opposite side. Okay, so we are going to call these things domains of electrons. Or really, what they are, they're just kind of like regions. Regions of where electrons actually are. So these domains are going to be attached to a central atom, and they're always going to get away from each other as much as possible. So a lone pair is equal to 1 domain or 1 region of electrons, because as you can see here, it's off to the right. It's like its own little thing attached to the atom. A single bond is also equal to 1 domain. A double bond, although more complex, it's still confined, right? So a double bond is going to be very similar. So if I have an atom and it is double bonded to something else, it's still just kind of held between these 2 positive charges, right? So it's still held between the positive charge on either of those, and that is also going to equal 1 domain. So 1 region of electrons. Although it's more complex and it's a double bond, it still counts as 1 domain. And I think you see where I'm going with this. A triple bond is also 1 domain. Okay, so if I had a triple bond here somehow, it would be, again, opposite the other pair of electrons. So electrons, these different domains are always, doesn't matter what type, they're all count as just 1 region of electrons, and they're going to get away from each other as much as possible. Okay, so when we have these different domains of electrons, anything counts as 1 domain. So there's a couple of situations that we can run into. When I have 2 domains, we've already seen a couple of examples of it. Let's say that I have my central atom here, and I attach now we're actually going to put some real things. Let's say I attach a hydrogen atom to it. Okay, actually, I'll just stay with just a regular atom. Let's say I attach something to it. If I want to put another pair of electrons or another domain on there, it doesn't matter if it's a double or triple or single bond, it's going to move as far away from that one as possible. They're going to be opposite one another. This right here is they're going to be as far away from each other as possible, meaning they're 180 degrees apart. Anything that's 180 degrees from one another, in this case, we have 3 of them. This is known as linear. So anything with 2 domains is going to be a linear configuration 180 degrees from one another. If I were to add another domain up here, so if we're going to get to 3 domains next, so when I get to 3 domains, what kind of electron configuration am I going to have? So if I put one here, these 2 in response are going to move. So by putting something there, these 2 are going to move downward, right? They want to be as far away from one another as possible. So if I add one here, these 2 are going to move down to that angle. Okay, so what this looks like is, all right, so if I have this central atom still, and I add one to the top, the other 2 are going to move away as much as they can. I can get this. Here we go. There we go. Okay, so they're going to move away from one another as much as possible. And now they were 180 degrees, but we've added an extra one in. Now they're 120 degrees. 120 degrees apart. And we call this trigonal planar. It all is on the plane of the paper, right? Looks like a triangle. There's 3 of them, and it looks trigonal planar. So trigonal planar is the shape. Okay. Where would I add a 4th domain? Where am I going to add a 4th domain to this? Well, I could add here, but that's going to be 60 from a neighbor. So what I really want to do is I want to add it up top here. So I'm just going to rotate this. So I'm going to rotate this thing 90 degrees and see what it looks like. So here's my central atom. And I have 1 and 2 and 3. So let's say that now these are all happen to be like in the same plane. Okay, so if I rotate this thing, bring this down to basically, or I guess bring this down to here, and then these are all, so if this is all on the plane of the board, now this is the piece of paper. It's like if I picked up the piece of paper like this and looked directly at it. So now I have this shape. What we're going to do is I'm going to add the one on the top. So I'm going to add a new domain on the top because that's 90 degrees from everything. And these are all 3 of these are going to kind of fold downward. Okay, so what's going to happen is when I add that one on top, these are all going to come down a little bit, and it's going to create a new shape. So the one, here's my central atom. I added the one on top, one here. I'm going to draw a little bit weird shape here and here. Okay, so what we see is this one, and I can label it. This is coming out of the board or out of the paper or out of the screen. There we go, screen. It's coming out of the screen at you, okay? This is going into the screen. These are both called stereo bonds. It gives you a shape, right? It gives you some sense of 3 dimensions because now we've moved into 3 dimensions. One is coming at you, the one is going away from you, one's in and out of the board. Regardless, every single one of these is the exact same distance apart. They're all 109.5 degrees apart, and the shape of this is called tetrahedral. So whenever I have 4 things attached to an atom, it's going to be a tetrahedral arrangement for most cases, right? When I have 4 domains. So tetrahedral. So those are the shapes that we get based on attaching things to a central atom. Okay, so that gives us, all of these gives us the electron shape. The electrons with 2 domains is linear. Electron with 3 domains is trigonal planar. The electron shape with 4 domains is tetrahedral. So when we decide how many domains, it locks us into one of these shapes. And so we're going to create a chart that's going to give us kind of some sub shapes based on how many lone pairs are present. Okay, so let's take a look at these different actual shapes. And this is really what we want to get to. So two domains. If I have two domains, again, it's going to look like we created. There's my two domains. The electron shape is going to be linear. Two domains, electron shape is linear. And I'm going to ask two questions. How many bonding and how many non-bonding? The non-bonding one is going to be the most important question. Domains. So how many bonding and how many non-bonding domains do we have? Okay. So when I have two bonding and zero non-bonding, okay, the molecular shape is going to be the central atom with the two things attached. This is going to just simply be linear. Nothing changes, okay, from the electron shape equals the molecular shape when we have zero non-bonding. This goes for all four of them. Okay, next up. So let's take a look at what happens if I move up to three domains. Again, we have the shape. There's my central atom. I've got three things attached. And we know that it is trigonal planar. In this case, I have three bonding domains, zero non-bonding domains. So let's write out what that shape looks like. Again, it's going to be the same exact thing as what I started with. This is going to be trigonal planar. Again, if there are zero non-bonding, the domains equal the electron shape equals the molecular shape. But I can take this, and we're going to do this a little bit backwards. And let me just, this is non-bonding again. And this is bonding. These are domains, right? This is electron shape. And this is shape at the end. If I replace the top one here with a pair of electrons instead, so we have a lone pair of electrons. Okay, that pair of electrons is still doing its job, pushing those two, still doing its job, pushing those things down. That didn't disappear, but what we can actually see, what you can actually see in the chemical world is this shape. This is what we see in spectroscopy when we're looking at molecules. You can't see electrons. You can see things with mass, so you can see atoms, but you can't see anything else. So what you can see is just that shape. This shape is known as bent. So when I have two bonding and one non-bonding, what I actually see is this shape known as bent. Okay, so what you see is everything but the electrons. So if I have one non-bonding, so if I have one lone pair on something that is three domains, it's known as bent. Okay, next up, or last up, I should say. What happens if we move to four domains? So four domains, and this is as far as we're going. We can go up to six. What is the electron geometry? Non-bonding. Or I guess bonding is first, right? Yeah. Bonding versus non-bonding. And molecular shape. So four domains, again, that central atom with the four things attached. We have the little stereo bond. We know that this is tetrahedral. And four bonding, zero non-bonding gives me the shape of the same exact thing. We have a tetrahedron. Now, what happens when I take that tetrahedron and I replace the top of this with a pair of electrons? I can't see those electrons. So in this case, I have 3 bonding domains and 1 non-bonding domain. So what's the shape? So we know that it is tetrahedral when everything is there. When I replace a bond with a lone pair of electrons, this is now called trigonal pyramid, because it looks like a pyramid, right? So we still see that shape. We still see basically those things are downward. Okay. What happens when I replace 2 of these with lone pairs? And because it's going to be easier to see, I'm going to replace those 2 with lone pairs. So I'm going to replace both of these with lone pairs. So I have a lone pair coming out at us, and I have one kind of going back into the board. Right? So they're the same size, just one's going into the page, one coming out of the page. We now have 2 bonding and 2 non-bonding. So when I have 4 domains, 2 of them are electron pairs, the shape that we see is now bent. So we have 2 bent. We have 120 degree and 109.5, but those are the shapes that we see. So this table, you're going to have to understand how to create, or you're going to have to memorize it. But we are able to get shapes based on our structure. And so let's do some examples based on this. So if I were to draw out some Lewis structures, and you can pause this and do the Lewis structures and see if you can get them right. So let me try, let's say CF2Cl or H2. Let's try PH3. Let me do OF2 minus. And we're going to do, let's see, what else? CO2 and O3. I want to know what the shapes of all of these are. So go ahead and pause and try to do the Lewis structures, but I'm going to really draw them really quickly. In fact, I'm going to pause this. I'm going to draw them out so you can check your answer. Okay, so this is what we got. These are the shapes that we have. So if we look at these one at a time, we're going to be able to come up with the molecular shape of each of these. So let's take a look at CF2H2. So here we go. So how many domains do I have? 1, 2, 3, 4. I've got 4 domains. I have 0 non-bonding. And so now we're going to go up to our table. So if I have 4 domains, 0 non-bonding. So 4 domains, there's 4 domains, puts me in this category. And that's the shape. I have something that is tetrahedral. Okay, so 0 non-bonding in 4 domains gives me a tetrahedral shape. Therefore, this is going to be tetrahedral. Okay, so I encourage you to try the next couple, or when you're comfortable, pause and try to do the rest before I do them. Let's take a look at PH3. And so that's it. That's the start of this one. And we're going to talk about polarity in the next video. Let's take a look at PH3. So here's my shape. I have, again, 4 domains. A lone pair counts as 1 domain. Doesn't matter, always counts as 1 domain. Single bond, double bond, triple bond, still 1 domain. Lone pair, 1 domain. So 1, 2, 3, 4. So that's 4 domains total. So 4 domains. Again, we're going to be in the same category. But this time I have 1 non-bonding, or 1 non-bonding pair. So 1 non-bonding. I'm going to start doing ND for this, by the way, just to make things a little bit faster. So 4 domains puts us in that category. Come on, there we go. Slowly responding here. 4 non-bonding, or 4 domains, and 1 non-bonding means my shape is trigonal pyramid. And so there we go. This one is trigonal pyramid. OF2 minus. So that's the shape I have for OF2 minus. And we're kind of sensing a trend here. I didn't mean to do it this way, but here we are. 1, 2, 3, 4. Those are lone pairs, though. So that's 2 domains between those 2. 3, 4 domains. And there are 2 non-bonding domains. What shape does that give us? There it is. 4 domains, 2 non-bonding. 4 domains, 2 non-bonding gives us a shape of bent. So here we go. This right here is bent. So bent, trigonoplanar, tetrahedral. Great. And so the next one. On this, I've got 2 double bonds. How many domains is that? That's 2 domains. Again, don't count the domain, don't count the pairs, the bonds, doesn't matter. Double bond, single bond, triple bond, still 1 domain. 2 domains, 0 non-bonding. If you look up above, you're going to see that this is also linear. Okay, so this is linear. And then move to the last one. Here I have 3 domains. A, 3 domains, 1 non-bonding. This is going to give us a shape of bent. Okay, so that's it. That's how we do it. We count the number of domains and we figure out what shape we have based on the table that we created above. Great. So that's it. That's how we do these things. Give them a try. Let me know how you're doing. And then the last thing we're going to cover is polarity, and that'll be in the next video.